this work, we address the challenges associated with conserving moisture in sandy soil and arid regions. When the water holding of soil is low, the agriculture becomes less efficient and the soil erosion is intensified.
With sandy soils, water can easily permeate past a plant's root zone, resulting in low water use efficiency. There have been many successful solutions to improve this issue. However, they can require significant resources and time to be effective. What we are proposing is a material that would provide an immediate improvement to water conservation. Our solution is a macroporous hydrogel polymer that acts as a passive water reservoir for plant life and microbes in the soil. Hydrogels are not a new concept to agriculture. Superabsorbent polymers were discovered decades ago and have been implemented since, because they do show very high water uptake potentials. However, there are some drawbacks to these polymers. Their water holding potential can be higher than what plants are capable of removing. This is because the water is held within the polymer matrix. The water uptake can also be influenced by environmental factors such as pH or salinity, and these polymers do not degrade over time.
Another problem with conventional hydrogels as soil amendment is that their water uptake kinetic is very slow. Therefore, they are not efficient in arid regions with seasonal flash floods.
Our material is both functionally and structurally different. We made a biocompatible hydrogel polymer that potentially can be biodegradable. We formed our hydrogels as a macroporous structure using what's known as high internal phase emulsion templating to achieve a porosity of up to nearly 90%. Due to this low density, our porous hydrogels can be added at a much higher volume than common superabsorbent polymers with the same weight of material being added. The water availability is also significantly improved because we are holding water not only in our polymer matrix, but also in a more easily accessible porous structure.
The interconnected porous structure in these templated hydrogels accelerate the water uptake through capillary action. In fact, water is stored in both the polymer network and interconnected porous structure.
The results of our work shows that the porous structure increases water uptake over 700% compared to our non-porous hydrogel material, and we can reach a maximum swelling within 1 minute of immersion in water. We also found that influences of salt and pH on the water uptake were negligible, since the majority of our water uptake was through capillary action. We also saw the porosity increase the water release at 3.5 times, indicating a higher water availability.
The emulsion templating method enables us to make superabsorbent polymers from biowaste and biomass because most of these biopolymers do not have a very high water uptake kinetics and capacity to be used as superabsorbent polymers.
I would say the most exciting aspect of this work is its potential. We are not formulation limited here. We use the high internal phase emulsion templating method to create our porous network, but it can be applied to many other different polymer systems that are capable of being emulsified. We could change the polymer formulation to improve hydrogel's biodegradability, its structural integrity, or even its affinity to water.
I believe this work offers a sustainable and environmentally friendly replacement for the current superabsorbent polymers.
So there's quite a number of systems that we could explore for this application alone, and we look forward to its development.